Hi, welcome back to the lecture series on GPU architectures and programming. So, I believe in the last lecture we have been kind of discussing more on concurrent kernel execution and how concurrent kernels can be mapped to an underlying OpenCL device. So, in that context we talked about the following possible options, like if you have concurrent tasks, then one option can be that you have these tasks are all different kernels which are coming from different independent applications. So, they do not have any dependency, and so also the other option is that, well, there is the same kernel, but multiple it is the same application, but from that same application multiple kernels have been launched and they do not have really any dependency among each other. So, then you have them, you can just run them concurrently across multiple devices. Also, suppose you have one kernel and you want to exploit more compute capabilities of the hardware, another option can be that you partition the kernel across multiple devices and execute them. So, there has to be some motivation, like why you will want to do that. We'll discuss on the motivation. So, in general, you can have, as we are discussing, that you have this multiple kernels, or multiple kernels of the same application, or they belonging to different applications, they are executing concurrently. But in case you want to increase the concurrency more, one option is, in case you have also available devices, you partition the kernel across devices. But issue is, how can it really be done? First of all, the good thing about doing it is that you can exploit both CPU and GPU devices by using both the devices to kind of execute the same kernel, and this is one advantage that OpenCL has, right? Because an OpenCL kernel does not make a distinction between CPU and GPU devices. It is built in for heterogeneous computing. So, you can actually split the kernel into two sister kernels, I would say, and dispatch them to multiple devices. And of course, the two devices have to be available in the system for doing that, but assuming they are available, then what is happening is you are exploiting more amount of parallelism in that way, and this can really be done using OpenCL's data transfer APIs, query, memory objects, and and the support for multiple devices that is available. So, to motivate a bit more, in general, you can have kernels which are GPU friendly kernels, I would say, because let's say the kernel has too much of parallelism, and inside each parallel thread there is not much of control oriented dependency. So, then it is a very much GPU oriented kernel, and it makes sense to execute in the GPU. Whereas you may have an OpenCL kernel with lot of branches, divergences, and control dependencies inside the kernel. So, that would make a case for CPU only execution. So, overall you have a design space, like whether you want to execute a kernel fully in the CPU, whether you want to execute the kernel across CPU and GPU, or whether you want to execute the kernel fully in a GPU. So, just to create a problem space here, this is what we can do. Like, suppose you have this kind of a kernel, and you are trying to submit, and this is the full job. This is the full data space on which this kernel K1 is going to work. So, it is essentially defining a transformation which will be carried on the entire data space. You can dispatch that kernel to the CPU and get the work done on this data space. You can dispatch it on the GPU. You can get the job done on this full data space, or you can split this data space to individual memory segments and get two kernels spawned. One kernel dispatches to CPU, one kernel dispatches to GPU, and then you have both of these devices engaged in parallel for doing the job, which is a good thing, right? If you dispatch it only in CPU, the GPU is idle, in case there is no other application or some other kernels which are running here, right? But in case this is free, there is no other kernel which is looking to execute here, then why not you split it like this and execute some part on the CPU and some part on the GPU. So, we will first try to figure out when and how these things make sense. So, this is the primary motivation, that it may happen that some other devices are available, they are idle. So, it makes sense to partition the data space and dispatch multiple kernels on the partitions data space across engaging these multiple OpenCL devices. And effectively what you are doing is you are kind of exploiting the system's available concurrency more efficiently. But let us also discuss when and how this thing makes sense. So, suppose you have this data space and you have, so let us say this is the host memory, and since it is attached to the CPU device, so right. So, you are bringing the data to the CPU's cache and then you are executing it on the CPU's pipeline here, and then you have an off chip connection to the bus, and on this bus you have a connection to the GPU memory, let us say the device memory, and the device in general. So, this is like the entire device, there may be multiple such devices. So, what is the overhead of actually partitioning the data space and executing in the CPU, or I mean across the CPU and the GPU. So, if you do a CPU only execution, there is no data transfer involved, right. So, you launch as many, I mean your OpenCL kernel will launch as many threads as the total number of parallel SIMD operations supported by your CPU, and those threads will actually execute in parallel and they will compute on this data space. So, if it is a branch heavy kernel, I would say, then makes sense to have it in the CPU. By computational nature, it is a CPU friendly kernel. So, then it makes sense not to send it to the GPU. Why? Because first of all, GPUs are not very efficient, they do not have such speculative execution and other supports that you have in CPUs. So, for handling branches, the CPU as a device is much more efficient. Now, when you are thinking of executing on the GPU side, then you have the problem, which is that this is then you have the host program which is executing on the CPU. This host program has to first copy the data from the host side memory, which is this one. You have to copy the data from this host side memory to the GPU's DRAM, which is here, right. So, that is some additional data transfer overhead that you have. So, from the memory that is referenced by the CPU, you have to first define buffers in this memory, and you have to copy the data into this memory. Once the input buffers are set up, then you are going to launch the kernel, right. So, let us say the CPU only execution time for a kernel is EX CPU, the GPU only execution time for the kernel is EX GPU, and let us for the sake of generality assume that in total you have 100 threads, and if you are working with x number of threads, let us say a factor of x, then the execution time in the CPU would be x multiplied by EX CPU and the rest of the threads. So, let us say you have 100 minus x threads which are executing in the EX GPU, assuming that you are splitting this number of threads in parallel across the devices. Question is, when will I do it? I will be now the issue is there is this data transfer time, right. So, this factor x I have to choose in such a way that the execution time x for x number of threads in the CPU should actually equal the execution of time of the rest of the threads in the GPU plus the data transfer overhead of this 100 minus of the requisite memory elements for this 100 minus x threads, right, because you have to send these many elements to the GPU's memory and you want to do the compute, right. So, then I would be able to say that let us say the original execution time is this, or in the GPU it is this, but when I partition it, the execution time becomes equal to this x multiplied by this AX CPU, right. So, just a small correction let us do here. So, if we are saying that x is a factor, so it is like 1 minus x. So, you multiply it by 100 here and you multiply it by 100 here, right. So, let us say x is 0.2, that means you are executing 20 threads in the CPU and the rest of the 80 threads in the GPU, and you are if in case it happens that executing 20 threads in the CPU takes same time as the time required to copy the 80 threads corresponding data elements to the GPU, copy it back and also do the operations, then this is the execution time that is required, right. Now, it may so happen that the data transfer overhead is too high for some kernel. In that case, this is not a good option, right, because if the data transfer overhead outweighs whatever benefit you can have through parallel execution, then this does not make sense. You will only like to you will only like to bear with this data transfer overhead if the available parallelism for whatever threads you are now launching in the GPU is much more with respect to this overhead, right. Otherwise, this kind of execution will not make sense. But this is for the kind of devices where we have a discrete GPU. So, let us say you have an Intel CPU, an NVIDIA GPU or some AMD GPU, let some other vendor's GPU, they are connecting through a PCI Express bus. So, both are separate chips, right. Now, in that case, this is the execution timing, some possible, again these are all very, we are making lot of assumption here. We are saying that the execution time is proportional with the number of threads and all that. And so, and also since this is a factor, so and this is the execution time for 100 threads, so we can remove it, it is just x multiplied by this and 1 minus x multiplied by this. And but as we are saying that for a integrated GPU, this execution model is not going to hold, because here we actually capture the data transfer overhead. Now, the question is, what is an integrated GPU? Well, you have modern CPUs and other devices from different vendors, where on the same die you can have a CPU device and a GPU device and also a shared memory, right. So, there is no data transfer overhead when you are defining buffers for this class of devices. So, when you partition kernels for this class of devices, the data transfer overhead is not there, so the calculations have to be done in a different way. So, all this points to the idea that maybe in certain cases it makes sense that you really partition the data space and launch multiple kernels in case you have multiple devices which are freely available in the system. Okay. So, with this motivation, if we go forward here and let us see how really this can be done. So, in this classic example, what we are really trying to say is, let us break K1 into two parts. So, you split that in a way that x number of threads go to CPU, y % of threads go to GPU, total is 100 here, and accordingly you create two different kernels, one for the CPU and one for the GPU. And let us say for the system, the CPU only execution time is this, the GPU only execution time is this, but if I split and execute, since I have some parallelism, they will execute in a shorter amount of time. So, here the overall execution time was this, because up to this point the whole job is not done, and in GPU the overall execution time was this. So, this is like a picture for a GPU friendly kernel. That is why I make a small split just to load balance, since this is anyway a GPU friendly kernel. I send smaller number of threads to the CPU and more number of threads to the GPU, so that after this much time both of them are getting done. Okay. So, let's take an example of such a piece of code. Consider this idea of how you can as a programmer partition a kernel into two kernels for execution in parallel. Of course, you can write a tool which will automate this transformation. You can write a compiler kind of tool which will take as input a kernel and take a partitioning factor and create multiple kernels for multiple devices which can execute in parallel. Now, one important thing I would like to say that when we are assuming we are doing this kind of partitioning, we are also thinking that there is no dependency among data in the data space. So, when I launch a thread, we are thinking that the kernels are such that the thread does per unit data computation. So, the ith thread, let's say, is working on elements from ai and bi in the input buffers. So, the ith thread is not accessing, let us say, ai and ai minus 100. That will actually complicate the splitting process, right? So, of course, in that case also you can write a split code, but in our examples we are making that simplistic assumption just to motivate the idea here. So, here we will show an example where you do vector addition of two vectors whose size is of length equal to some constant, and you partition across one CPU device and one GPU device. You create two separate contexts, one for each device, and send 20% of the threads to the CPU and 80% of the threads to the GPU. So, initially, this is a simple code, right? It's just that you are just doing a partitioning of the data space and executing across devices. So, you have a data size, and corresponding to that, you initialize three vectors in the host, three buffers for storing the input vectors in the host memory, right, and also the output vector space. Now, so you initialize the two input vectors HA and HB, and then you create suitable data spaces for for partitioning. What you do is you calculate what is the data size for the CPU and for the data size of the GPU. So, assuming we are doing an 80 and 20 split, then you need to create suitable buffers in the CPU memory. So, what we do is you create using CL create buffer, you create a buffer in the CPU memory inside the context of the CPU, right. So, you create in the context of the CPU. So, here again we are assuming that all these devices have been nicely set up, and you are just having two contexts set up, one for a CPU device and one for a GPU device, right. Also, we are assuming that the host program is not running in any of them. That is why we will actually be transferring data to the CPU and the GPU both, right. So, you do a CL create buffer for using which you create a buffer in the CPU for storing data of the size of the partition that you have defined. This is the size of the partition in the CPU. Similarly, this is the size of the partition in the GPU. You create a buffer in the GPU side, right. So, these are the three calls which are all on the CPU side for creating three buffers for the CPU, two of the input buffers and one for the writing the output data in the CPU, right, using CL create buffer. As you can see, for all of them the context is CPU and the buffer size is data size CPU, which is calculated here. And since these are input buffers, so they are in read only form, and once this is done, you also do the same thing on the GPU side, the GPU device. Again, we will just repeat, we are assuming the host programming is not executing in any of these devices. That is why you have to create buffers in both of these devices. So, you in order to set up the problems for the GPU device, you also create the input buffers and the output buffer where it will write the result, and then you do the data transfer of data size underscore CPU amount into the CPU device, and this is the command queue of the CPU, command CPU, right. So, you set up the two input input vectors, input buffers of size. So, these are the buffers DS CPU and DS GPU, both are the input buffers DS CPU and DB CPU, which are of size data size CPU, right, and they are essentially taking values from HA and HB, which are the original input arrays sitting in the host side memory. And then you do the thing that you just do similar write buffers for the GPU device. So, again from the host side memory, you copy data of data size GPU to the GPU device. As you can see, you are copying both from HA and HB, but you are copying from an offset, right? Because starting from the HA address, you have already copied data up to data size CPU. So now you copy with an offset of from HA plus data size CPU, right? And the amount of data you copy is data size GPU, right? So this is how you do it. So you execute, and essentially you are enqueuing these write buffer commands. So you have enqueued these two write buffer commands here to the CPU device. You have also enqueued two write buffer commands to the GPU device. Once this is done, you have to execute and read the outputs from the devices to the host. So first you execute the kernels. So you have to execute the kernels in the command queues of by enqueuing suitable kernel launch commands in both the command queues of the command CPU as well as the commands GPU. So as you can see, we have two enqueue ND range kernel calls, one for the command CPU queue and then for the command GPU queue. So once this is done, then the host program will like to copy back the results from the two output buffers that have been set up in the CPU and the GPU device. So those are the buffers DC CPU and DC GPU. So you copy them back again by enqueuing suitable read buffer commands into the individual command queues of the CPU and GPU device. So once that is done, you will want to synchronize and flush the command queues of both the devices, right? So just to ensure that all the commands have been dispatched for both the devices, and finally you test the results. So that would be our idea of doing the partitioning of an OpenCL program. And as you can see that we have already explained that what is the situation in which you have some advantage. First of all, the data transfer time should be such that it's not too heavy, but you are doing enough work in the GPU in parallel to hide the data transfer time, and overall you have an advantage by exploiting the parallelism. So that also depends on the style of the kernel. So what if the nature of the kernel supports this part, is such that partitioning gives you an advantage and you have multiple devices available, then it may make sense to do the partitioning. Also, as we said, it may happen that you have devices, let's say you have several devices like modern mobile SoCs, where you have SoCs with on-chip CPUs and GPUs, multiple CPU devices, multiple GPU devices available with shared memory based interface, with shared memory interfaces, so that they can just copy data quickly across the shared memory. They can produce their outputs and write to the shared memory, right? So there is no question of data transfer overhead for such kind of devices, and their partitioning also doesn't have too much overhead with respect to the data transfer. So depending on what kind of device you choose, you have to select whether we have to first decide whether partitioning is actually helpful, or is the kernel is very much CPU friendly or very much GPU friendly. I would say that it doesn't make sense to partition. There are kernels with different kinds of characteristics. So you have to understand the characteristics of your kernel, whether it's a branch heavy kernel or compute heavy and parallel kernel, and also whether there is enough number of independent processing for each kernel thread so that the data space can be split nicely and dispatched across devices. So you may gain depending on the kernel characteristics by exploiting the parallelism, provided you have multiple devices available. So that is the advantage of partitioned execution of OpenCL programs, and with this we will like to end this lecture. Thank you.